So what we're going to do first here is kind of see the breakdown of these rules that we'll then define, and then we'll get some practice using them. So what I want us to do in this first example here is just compare the outcomes of these two. So taking logarithm base 2 of 32 compared to log base 2 of 8 plus log base 2 of 4. So log base 2 of 32, so my question then there is 2 to what exponent would give me 32? So the answer to that would be 5. Now, as we get into kind of, I don't know about complicated, but as you go searching for these exponents, if you're unsure, what you can always do is use a calculator to help out. So like if I know I'm working with base 2, I could go 2 and then set up an exponent and then just plug in until I find my value. 2, no, 4, no, 5, where am I at? Sorry, 4, 5, okay, there's my 32. So if you're dealing with more complicated numbers, larger numbers, you can always set up the base and then just start plugging in exponents until you reach the number that you need. And then our solution is that exponent right there. All right, so there's one side of it. Now let's look at log base 2 of 8 plus log base 2 of 4. So I'm going to evaluate these separately. So log base 2 of 8 is saying 2 to what exponent is 8? And that would be a 3. So in substituting values into expressions, the idea is that all of this notation right here changes into just a number 3. So what we're doing is making a replacement of all of that with just the number 3. Log base 2 of 4. So 2 to what exponent would give us 4? Well, that would be a 2. And then in between those two numbers, we have addition. So as we go through these examples, I'm going to really emphasize substituting correctly, because with this new notation of logarithms, sometimes it gets jumbled up or these numbers start doing things. But really all of this notation here is connected. It's all one unit. And then we're just replacing it with an exponent. All right, 3 plus 2 is 5. So what I want us to notice here is we get the same exact thing out. That log base 2 of 32 is the same thing as the addition of those two pieces. And the other piece that I want us to notice here is that 32 is made up of 8 times 4. So through all of this, we have log base 2, which is great. That base should stay the same. But seeing it separated in this longer form, what we could do is combine it to a single expression, just here, by multiplying those input values. So what we could do is take, if there's addition between the two numbers, we can combine them into a single logarithm of base 2 by multiplying the inputs. We could also move in the other direction. It's a little more difficult, but if we needed to split this up, you can split this up into two logarithms using factors of 32. So like we could do 1 and 32, you can do 2 and 16, so you can choose numbers that would substitute in there using factors of 32. So what we get from this is that there's this kind of change between taking log base 2 of 8 plus log base 2 of 4 and converting that to log base 2 of, and then inside parentheses, 8 times 4. And we can move in either direction with this. One thing we need to get straight with our operations is that what's happening with these is addition on the outside of the logarithm, and over here it's multiplication inside the logarithm. So I'll keep emphasizing that as we go through these, but that's the connection. Multiplication inside the logarithm relates to addition outside the logarithm. So we'll talk about that more. Let's look at this next example. So log base 3 of 9, so I'm thinking 3 to what exponent gives me 9, and that exponent that I would need is 2, because 3 squared is 9. Over here, log base 3 of 27, so 3 cubed would give us 27, so I need that exponent of 3. And then minus, and log base 3 of 3, that's our identity rule, where those numbers match up. That means we need an exponent of 1. So 3 minus 1 is 2. So what we're seeing is this connection where these two pieces are exactly the same. And the other piece I want us to notice is that 9 comes from 27 divided by 3. So what we're seeing here is this relationship to division of these two numbers. So with addition, it came through as multiplication. With subtraction, it comes through as division. And specifically, it's going to go numerator on the left, denominator on the right. So what we're going to have is this rule where we can move between these two scenarios of log base 3, and it can be any base. As long as the base stays the same across all of these values, that's what's key. This expression with the subtraction is the same thing as log base 3, and then inside a calculation of 27 over 3. So the relationship is going to be, this is subtraction outside the logarithm, and over here, it's division inside. So, again, we'll talk more about that, but that's how we can kind of move between these two. Alright, our last piece here, well, not last piece, but our last example. So a trick we talked about is that when it's log base 10 and you have 1 followed by a bunch of zeros, you can just count how many zeros there are. So this would be a 4. But what we could do is think 10 to the 4th power is the same thing as 10,000. Because also that exponent determines how many zeros are showing up there. Now 4 times log base 10. So my logarithm piece is really all of this right here. So I'm going to keep that 4 multiplying on the outside. But what I want to do is replace this logarithm expression. So base 10 with 10 inside, that's our identity rule. So for those to match up, we need an exponent of 1. So 4 times 1 is 4. Now, what I'm going to do is one little extra step on this left-hand side here, where I'm just going to change this to logarithm base 10. Instead of writing 10,000, writing this as 10 to the 4th. And that's the 4th power. So what we're seeing here is we can have this kind of movement of the exponent where we have this exponent of 4. What we could do is take that exponent of 4 where it would usually show up and put it out front as multiplication. So to just kind of visualize that more, we have log base 10 to the 4th. What I can do is take that 4 and put it out front as multiplication, so that then we just have 4 log 10. So we moved our exponent and it becomes multiplication out front, and then we just have an exponent of 1 right there. So that's going to be a rule that we can follow as well. Alright, so a list of the rules we just talked about. We have, if we have logarithm base A and we're multiplying inside, so again, we want to be clear that we're multiplying inside. What we can do is separate that up with addition outside the logarithm. So when I'm saying inside and outside, like inside means within the parentheses, it's inside the logarithmic function, and then outside, it's an outside function. Like I would evaluate that logarithm, and then the last thing I would do is addition. And we can move in either direction with this. It'll just depend on what we're trying to do and how we're trying to simplify. Sometimes you might have this string of addition, and then what you can do is simplify by combining it all inside into a single logarithm. Or sometimes you'll just have a single logarithm and you want to break it up, and then you can move to this addition form. This next one was where we have division inside, and we can switch that to subtraction outside. So if we're seeing a fraction inside or some division of expressions, what we can do is split it up and just make sure it goes numerator minus denominator. And then our last piece is if we see an exponent inside, what we can do is move it out front. So if the exponent is inside the logarithm, it can move to outside as multiplication. That one's a little more difficult to write in terms of that notation that I was doing back there. So why I'm focusing on where it's inside versus outside is because sometimes you'll come across values where you think there's a rule for it and there isn't. And that's where, if this is your first time going through logarithmic properties, like I said, I'll have that printout that you can have as you work, and just keep referring to it. Work slowly, because sometimes you'll think there's a rule when there isn't. So what you should notice here, is what's happening on the outside of the functions, addition and subtraction. Keep that in mind of when those are on the outside, we have something we can do. Same thing if you're looking inside the function and there's multiplication, division. So a question might be, well, what if it's addition, subtraction inside the function? What if we mixed it up? So let's say we had log base 10 of x plus 3. And we wanted to know what we could do with it. And the answer is nothing. We can't do anything with that. That is stuck just like that. However, if I changed it to log of x plus log of 3, if I moved it to the outside of the logarithm, now I can use that first rule there. I have this two separate logarithms adding together, and I can combine them into a single logarithm of x times 3, keeping that same base throughout. So that's where I'm emphasizing this inside versus outside of the function, because there's going to be cases where we get stuck and you feel like there might be a rule to use, but there isn't. And that can be the most difficult part with these, is knowing when to stop using the rules and stop simplifying. Okay, so let's practice these. So with this first one, there's a few rules you could use here. Our quick rule would be that we have log base 4 and base 4 of our exponent. So that identity rule just said we would be left with our exponent of -5. So you could use that. If you wanted to use our new rule, what we could say is, well, that exponent of -5 would go out front. So we would have -5 times log base 4 of 4. And log base 4 of 4 is just 1, so -5 times 1 is -5. So we're going to get to this point where sometimes there's more than one rule that you can use, and they'll get you to the same solution. Alright, log base 8 of 16 minus log base 8 of 2. So what I could see here is if I tried to simplify it, so thinking 8 to what exponent would give us 16? Well, without a calculator and without a formula that we're going to talk about later, I can't do anything with that. So I can't simplify this number. Same thing with log base 8 of 2. That's tricky. So this is where we can look at the rules to help us out. So what we have is subtraction outside. So I'm just going to make a little note that we see subtraction outside the logarithms, which means we can combine these into a single logarithm. So how this combination goes is we'll have one logarithm, keep the base that you're working with, so we're working with base 8, and then of, and when it's subtraction, we're changing this to division. So it's going to go numerator, denominator, so 16 over 2, which means we have log base 8 of 16 divided by 2 is 8, Now we have an identity. If our base is the same as the value coming out, then we need an exponent of 1. So where these properties help us is starting with something that we can't evaluate, and we end up with something that we can evaluate based on those calculations. All right, with this one, and these questions here, I put a mixture of the rules from our previous video and this video that we're going through now. So this one doesn't really tie it to the product, quotient, or power rules, but it has our identity rule of base e for the exponent, base e for the logarithm. So our solution should just be that exponent of 2. All right, this next one here. Again, if I tried to evaluate these, I get stuck. So what I want to do is recognize that I have addition between two logarithms. So we have addition outside the logarithms. So what that means is I can combine them into a single logarithm. So we're going to have logarithm, keep that base of 6, and then because it's addition, we're going to multiply. So we have 9 times 4, which means we have logarithm base 6 of 36. And I just need to think 6 to what exponent would give us 36, and we would need an exponent of 2. All right, here we have our identity rule, base 2 of the exponent, base 2 of the logarithm, and that means those will just kind of cancel out with each other to leave us with 11. And here, we're very close to using that identity rule, base 5 of the exponent, base 5 of the logarithm. However, we have this addition of the logarithms, and that doesn't work. What we need is a single logarithm in that exponent. So what we can do is use our property that we have addition of two logarithms. So I'm still going to have base 5 of the exponent, but then what I can do is combine them into a single logarithm base 5, and then inside the logarithm is multiplication 6 times 7, which is 42. And now I can see base 5 exponent, base 5 logarithm, those will cancel out, and all we'll have left is 42. So, again, with these, take your time, and also going through a few examples in these videos, but be sure to check out the participation where we'll get a lot more practice there too.